All right, so on number 11 here, what do we want to do? So it says, suppose you put 7 names, Marky, Ricky, Danny, Terry, Mikey, Bob, and Will, into a hat, and you draw 2 names. In part A, it says, if you replace the names after each draw, determine the probability of drawing Will's name. Okay, so let's do A right here. And so the first thing we want to do is you have to understand the problem. Okay, you have 7 names, you put them into a hat, and you're going to draw 2 names. And you want to figure out the probability of drawing Will's name. So maybe the first thing we'll do is we'll just figure out the number of things in our sample space. All right, so remember, we're drawing 2 names, so you have 2 spots. And for the first spot, since you have 7 names in the hat, you have 7 choices. And now because you replace the names after each draw, you have still, the second draw, 7 choices. So here you have 49 things in your sample space. Now in your event space, E, okay, remember the event space is that you actually draw Will's name. So what we'll do is we'll break this up into cases, right? The first case will be that we draw Will's name in the first spot, right? In the second spot, we'll say we have just 6 choices instead of having 7, because we won't. In this case, we'll just say we don't draw Will's name. So the idea is we have, Will and Marky, Will and Ricky, Will and Danny, Will and Terry, Will and Mikey, Will and Bob. We're not going to count Will and Will here. So we have basically 6 names that we can choose from. Plus, the next case would be that we draw Will's name in the second spot. And again, we have 6 other names that we can put here if we exclude Will's name. And then plus, we have the one outcome where we have Will and Will. Right, so you can count these up. You have 1 times 6, so 6 here, plus 6 times 1, so 6 here, plus 1. And so you get 13 things in the set E. So the probability that you draw Will's name, if you replace names after each draw, is equal to the number of things in E divided by the number of things in S. And so you get 13 over 49. And so that's my answer. You can check this on your calculator to see what the percentage would be. So 13 divided by 49. All right, so or you get about 26.5% of the time. All right, then in part B, it's a little bit different. So in part B, it says if you do not replace the names after each draw, now determine the probability of drawing Will's name. So let's look at S now. There's slightly fewer things in S because you still have 7 choices for the first spot, but for the second spot you only have 6, right? Because you're not going to replace the names, so you only have 6 choices for the second draw. And so this is equal to 42. Right? 7 times 6. And then for the number of things in E, we do the same thing. We're going to do some cases. So you say, okay, I drew Will's name in the first spot. I get 6 other choices for the second. Plus, instead of drawing Will's name in the first spot, I'll draw it in the second. And I have 6 names for the first. But you don't have this plus this 1-1 case, right? Because you can't draw Will's name twice, because if you draw Will's name once, you don't replace it. Right? So you just have 6 plus 6, so 12 possibilities. So now the probability that you draw Will's name when you do not replace is equal to the number of things of E divided by the number of things in S, which is 12 over 42, which we can simplify to 6 over 21. And on your calculator, you can do this. Oh, and actually, this can be simplified further, right? So let's fix this. Right, so this was 6 over 21. So I just realized that 3's going to this, right? So this is actually 2 over 7. Right? 3 goes into 6 2 times. 3 goes into 21 7 times. So you get 2 over 7. Or we can figure this out on our calculator. 2 divided by 7 is actually 28.6% about. All right, so what can we conclude from these 2 results? If Will wants his name to be drawn in one of the 2 spots, which option should he take, right? Should he have them replace the names or not replace the names? And I think Will should pick do not replace the names because it's 28.6% likely his name will be drawn, whereas if you replace the names, it's slightly less, 26.5%. So I would go with B if I was Will and I wanted my name drawn. All right, on the next problem, okay, so now it says that Jenny currently has a 4 year car loan at 8% compounded monthly. Her payment is $225 a month, and her current balance is $7,356. How many payments has she made? All right, so there's a lot of information here, and now to do this one, we need to pull up. Oops, wrong one. So to do this one, we need to pull up what? We need to pull up our formula sheet. So over here, let's go down, and here's our formula sheet. You have to decide which formula you're going to use. And here you have compounded monthly, so you know it's a compound formula, so it could be number 2, but then it talks about a payment, right? So that gets us down here to future value and balance loan. And then remember, on this one it says actually how many payments has she made, and so this one is the only one that has K, which is the number of payments, so it must be a balance formula. So over here I'd copy this down, so copy down the formula. The balance B is equal to P times N over I, and I have 1 plus I over N to the NT minus 1 plus I over N to the K, all divided by 1 plus I over N to the NT. All right, so I'm going to take this away, and now what I want to do is I want to plug in the numbers into the appropriate spots. Okay, so let's see. So I can say the balance. All right, well the balance is currently $7,356. So $7,356 is equal to, P stands for the payment, which is $225. Right, N. Right, well what's N? N is the number of times you compound the loan. And remember, if you forget these things, I keep hitting the wrong button here. All right, so if you forget these things, what can you do? You can look at the formula that says N is the number of times interest is compounded in a year, and this is compounded monthly. Right, so now I know N is 12. I is typically pretty easy to remember. It's the interest rate, so that's 0.08. And then I have this 1 plus 0.08 over 12. So 12 times T. Now T is the number of years, and so that's 4 years, minus 1 plus 0.08 divided by 12 to the K. Now I don't know K. That's actually what I'm looking for, because it says how many payments has she made, and K is the number of payments. And then all divided by 1 plus, and I have 0.08 divided by 12 to the 12 times 4 in parentheses. Okay. Now I have to solve this equation. To solve this equation, what I need to do is graph the right, graph the left, and then intersect. So I take out my calculator, and I'm going to plug this in. So I have y equals. I'm going to clear out all this stuff because this is from an old problem, and I want to turn off my plot. So you see my plots highlighted, so turn that off. And then I need to plug in this 7,356. Actually, I'll plug that into y2. All right, first I'll graph the right-hand side. So I'll do 225 times 12 divided by 0.08. And then I'll do a left parenthesis. Right, so let me say a few things here. Right, so remember, you actually don't need this first set of parentheses. Right? This is just there to offset this quotient. What you're going to need in your calculator is actually to put parentheses on the top. All right, so let's put parentheses on the top here, like that. So when I go over here, I put left parenthesis for that parenthesis in green, then I put another left parenthesis for that one in red, and then I have 1 plus 0.08 divided by 12 in parentheses raised to. Now if I want to raise it to the 12 times 4, I have to put parentheses around that, but I know 12 times 4 is 48, so I'm just going to say raised to the 48 minus left parenthesis 1 plus 0.08 divided by 12 in parentheses raised to, and now this is my x, right? So instead of k I write x, and then in parentheses for the parentheses in green, and then divided by left parentheses 1 plus 0.08 divided by 12 in parentheses raised to. Again, if I want to put 12 times 4, I have to put that in parentheses, so I'll just put 48. I need to make my window, and so then I have to remember I'm looking for the number of payments. So I'll start with 0 for 0 payments, and I'm making monthly payments for 4 years. right? So that I can't make any more than 48 payments. Right? If you make a payment each month for 4 years, there's 12 payments in a year. For 4 years, that's 48 payments. And then I do zoom and go to zoom fit, and hopefully it gets me what I'm looking for. So I'll start my graph down here. I went from 0 to 48. Change my pen to red. I'm going to pause the video so it pulls up faster. Okay, we're back, and I graphed the formula right, but it looks like I forgot to actually graph y2. So go back to y equals and plug in y2, so 7,356, and then hit graph again. You'll see there a line goes across, and so you can graph it on here. All right, and then you're going to hit intersect to find where these two graphs cross, where they intersect. So hit second trace, go down to number 5, which is intersect, hit enter, then you just hit enter 3 times. At first curve, that's good. Second curve, that's good. Hit enter again, and out pops your answer. K is approximately 11. Right, and I bet you it's actually equal to 11. It's so close to it. All right, so 11 payments. All right, so the next problem, number 13, we're going to work with the Venn diagram and use this to answer some questions. So it says 100 college students were surveyed on whether they had taken college algebra, college mathematics, or calculus. The following was found. All right, so you can read through this. 35 took algebra, 25 college mathematics, 25 calculus, 10 college algebra and calculus, 10 college algebra and college mathematics, 15 college mathematics and calculus, and 5 took all 3. And then we want to answer these questions. How many students in the survey took college algebra but not college mathematics, took calculus only, took exactly 2 of these courses, and so on. Right, to answer these questions, without using the Venn diagram is rather complicated. But if you can use this Venn diagram properly, these questions become real simple. So the idea is you have basically a college algebra circle, a college mathematics circle, and a calculus circle. Right? And so what we can do is you start in the bottom, right? 5 took all 3, so I put 5 here representing 5 students took all 3. Then 15 took college mathematics and calculus, so over here is the college mathematics and calculus part of the Venn diagram, and 15 did it, so I already have 5 in there, so I just put 10. Right? So now 15, it says, took college mathematics and calculus, and only 5 took all 3. And then it says 10 took college algebra and college mathematics, so that's this piece right here, college algebra and college mathematics. I already have 5, so I put 5 here, so they add up to 10. And then above that, I have 10 took college algebra and calculus. So again, I put 5 here because I already have 5 in the middle. And so total, I have 10 in both of these, in college algebra and calculus. Then 25 took calculus, so I have 5, 5, and 10, so I just put another 5 here. 25 took college mathematics. I just put another 5 here because I have 5, 5, and 10, which is 20. Now 5 is 25. 35 took college algebra. Well, I have 5, 5, and 5, so 15. To get to 35, I need to have 20 there. And then I simply read these questions and use a Venn diagram to answer them. So it said took college algebra, but not college mathematics. All right, so here's all the college algebra people, and I want to exclude these people because they took college mathematics. So I get, what, 20 plus 5, which is equal to 25 students. Took calculus only. Right, well, here's all the calculus people, and only 5 of them right here took calculus only. So I have 5. Took exactly 2 of these courses, so 2 of these courses, and exactly, it's just this number and that number and this number, not the 5 in the middle. These people took exactly 3 of these math courses, so I have 5 plus 10, which is 20, right? So 5 plus 10, which equals 20. Took just 1 of these classes, right? So that's this number here, right? These took 2, these took 3, these took 2, so I have 20, 5, and 5. So if I just take 20 and add 5 and 5, I get 30 students. And now here's where I have to start being careful to not take calculus or college mathematics. Well, That means I exclude all these people, so did not, so I don't want to count these, and I don't want to count these. So it looks like I have just 20, but remember I have to count the number of people out here. So to figure that out, what I do is take 100, and I take away all these. So I take away 20 plus 5 plus 5 plus 5 plus 5 plus 10 plus 5. And if you do this on your calculator, you'll see that this is actually equal to 45 students. And so did not take calculus or college mathematics. I agree, I have 20, but I also have 45 that didn't take any of these courses. So that's equal to 65 students. And then took none of these classes, that's the 45. So 45 students. And the next problem, right, so this says determine if the inequality is true or false. Make sure you show your work. So this is actually order of operations problem. Right? So remember order of operations, it's please excuse my dear Aunt Sally, where this is parentheses, this is exponents, this is multiplication, and this is division, this is addition, and the S here stands for subtraction. Right, remember addition and subtraction can go together, and multiplication and division can go together. And what we want to do is you start on the left and work your way to the right and do one step at a time. And so you want to start with the parentheses. So you look here and you look for parentheses. So you have these parentheses here. That means you start inside. And then inside you have two other sets of parentheses. And so you can start with either one and always start on the left because that's how we read from the left to right. So this is equal to the absolute value of 11 minus 15 is a negative 4. Just one step at a time. Copy down the rest. And it's greater than or equal to. Remember, this is greater than or equal to because less than looks like an L, right? So the other one is greater than. So that's less than and that's greater than. And then I have 99 plus, and I start with the parentheses, right? So plus 6 minus 2, which is 4, divided by 2. And then I reset and restart. So again, I start with parentheses, so I go inside here, and I start on the left because I have basically two sets in a sense of parentheses. I have absolute value in these parentheses here. And I say, okay, absolute value of negative 4 is just 4, and minus, just copy the rest down. Is bigger than or equal to, and so now I have 99 plus 4 divided by 2. Order of operations says I do division first, and then I can do addition, so it's 99 plus 4 divided by 2 is just a 2. Now I reset and do it again, so I go inside the parentheses, and I look for another set here of parentheses, so right there. And so this is going to be equal to, I have 4 minus 2, and I have 17 minus 5 times 2. So inside here, the order of operations says do the multiplication first. So I have 17 minus 5 times 2, which is 10, quantity squared. This whole thing squared is bigger than or equal to, and 99 plus 2 is 101. All right, so the right side's done. I just have the left side to finish. So again, I work inside the parentheses, and I have another set of parentheses, so I do this subtraction. So I get 4 minus 2 times 7, all squared, bigger than or equal to 101. And then inside here, I have subtraction and multiplication, so I do the multiplication first. So 4 minus 2 times 7 is 14. Quantity squared, bigger than or equal to 101. And then 4 minus 14 is a negative 10 squared, bigger than or equal to 101. And negative 10 squared, well, negative 10 times negative 10 is a positive 100, bigger than or equal to 101. And so now this statement is false because 100 is not bigger than or equal to 101. 100 is actually less than 101. Okay, the next problem we want to do involves another Venn diagram. All right, so here it says some doodads are mullets, all mullets are tails, all hops are mullets. Which of the following conclusions are valid from the above premises? Okay, so let's look at this. And we have some doodads are mullets. So I need a doodad and mullet circle. So let's do, here's a mullet circle. Let's do a doodad circle. So here's a doodad circle. And then right here, some doodads are mullets. So it could look like this. Here's my mullet circle. And that expresses this idea: some doodads are mullets. Yes, some doodads are mullets. All mullets are tails, and so what I need to do here is include the entire mullet circle, right, all the way around, right, including this piece here. Right, the entire mullet circle is a tails, because all mullets are tails, so mullets must fall inside the tail circle. And then all hops are mullets, and so to do that, express that idea, I can do this: draw a hop circle inside of the mullets circle. So now all hops, yes, are mullets. Which of the following are true? So for part A, some hops are doodads. So here's the hop circle, and notice they don't cross the doodad circle, so this is an invalid conclusion from the above assumptions. And then B, some mullets are hops. Well, here's the mullet circle, and the hops is inside it, and certainly, okay, so some mullets, yeah, are hops. Yeah, so this is a valid conclusion, right? Because you can see there are mullets. All hops are mullets, so that means then some mullets are certainly hops. Now, some tails are doodads. Well, here's the tails. And yeah, some tails are doodads, because over here, these are tails. Remember, the tails circle goes all the way around here, and it intersects the doodad circle, so C is also a valid statement. All right, then number 16. All right, so we're back to financial mathematics now. So it says your bank has offered you a 30-year loan at a nominal interest rate of 6%, compounded monthly. Your monthly payment would be $720. Use your calculator to fill out the table below. You should round your entries to the nearest dollar. So on the left, we have number of payments. And then on the right here, we have a balance of a mortgage, right? So payments, balance of mortgage, payments, balance of mortgage. And we want to figure out, what's our balance of the mortgage after 0 payments, 1 payment, 2 payment, 3 payment, 4 payment, 5 payment. And so what I'm going to do is I pull up the formulas here, and I know I have to use a balanced loan formula because it's asking the number of payments, and this is the balance, really. So it says, balance, balance. And so copy down the formula first. So B equals P times N over I, all times 1 plus I over N to the NT minus 1 plus I over N to the K, then all divided by 1 plus I over N to the NT. And now the rest of this is just plugging in the numbers for the letters. All right, so let's look. So the balance we're trying to find, so that's B. And then the payment was $720. N is the number of times you compound the loan, so N is 12, divided by the interest rate, which is 0.06. And then you have 1 plus, I was 0.06, N is 12. And then I have 12 times, and this is a 30-year loan, so T is 30, minus 1 plus 0.06 divided by 12. And we don't know what K is, right? K is the number of payments, right? So it's going to cycle, 0, 1, 2. So you want to leave K as just K, all divided by 1 plus 0.06 divided by 12, again to the 12 times 30. All right, so now I want to put this into my calculator and make a table. So I take out my calculator. Let's clear this. Let's go in here and clear all that and clear that. And to do this, what I'm going to do is enter this formula into Y1, so 720 times 12 divided by 0.06. And then remember, on here, you really don't need these parentheses. They're there for show to set out that quotient. But you are going to need, on your calculator, parentheses around the top. So your calculator knows that this is all on the top. And so we'll put that in there. We'll put left parenthesis for the green one, then left parenthesis for the red one, and then 1 plus 0.06 divided by 12. In parenthesis raised to. Now, I don't know what 12 times 30 is off the top of my head. So what I'm going to do is put left parenthesis and then 12 times 30. And in parenthesis minus left parenthesis 1 plus 0.06, right? That should be a 0 in front of that. Missed that 0. Right, 0.06 divided by 12. Okay, and then I'm going to raise this one to the k, so to the x, and then in parenthesis for that green parenthesis right there, and then divided by left parenthesis 1 plus 0.06 divided by 12. Right parenthesis raised to left parenthesis 12 times 30. End parenthesis. All right, now if I put everything in there right, I should be able to make my table. So hit second window to put up table set. I'm going to start at 0 and it's increasing by 1s. Then I hit second graph to pull up the table. It says table right there. And all I really need to do then is copy down the answers. Right? So I notice here, and I don't care about the change, so I'm just going to copy them down. So I have $120,090. And then on the next one, I have $119,970. Then I have $119,850. And then I move to the third payment, which I write over here, $119,730, $119,486, and then $119,364. Oops, looks like I skipped one, huh? Oh, I better be careful here. So I thought I was going down to 6, but looks like I messed up right here. All right, so did I get 2 right? 2 looks right, and then I messed up, I think, after that. So let's fix this. So this should be then $119,730. There it is. Then $119,608. Right, then finally $119,486. Right, so make sure you copy them down right. Right, so those are the right ones now. All right. Let's look at number 17. Okay, so state which events are independent and which are dependent. All right, so remember, independent events, the idea is the outcome of one event won't affect the probability of this other event occurring. So like rolling a die and drawing a card from a deck. I would say that those are independent events. Right, why? Well, if I draw, let's say, a 5 from a card of decks, it's not going to change the probability of me rolling a 3 on a die, or vice versa. But if you look at part B, right, drawing a name from a hat, not replacing it, then drawing a second name, these are actually going to turn out to lead to dependent events. And why is that? Well, if you draw one hat from a name and don't replace it, well, then you've changed the probability of drawing the second name because you have fewer choices in the hat. Right? So if you started with, let's say, 10 names in the hat, right, and you draw a name, you don't replace it, now you only have 9 names. So in a sense, you probably increase the probability of drawing a certain name. Right? So those are dependent events. Okay, so now we're back to mathematical modeling. So in number 18, it says, let the total yearly enrollment E in millions of students at universities and colleges in America be a function of the years T since 1965. Use the table below to answer the following problems. Okay, so in part A, it asks us how many students were enrolled in college in 1985. And so you have to remember in 1985, this corresponds to T equal what? Well, since it started in 65, 85 is T equals 20. So on part A, let's write it right here, what it's really asking us to find is what is E of 20? And that's pretty simple. You go in the table, and at 20, you see there's 12.247, and that's millions of students. So that's equal to 12.247. And there's a decimal there. Million students. All right. Oops. I'm going to do that. Okay, then in part B, what do we have? It says use linear interpolation to estimate the number of students enrolled in college in 1988. So in 1988, this is actually T equals 23. And to figure out this, right, so you're trying to approximate what E of 23 is. And to do this, you're going to use 20 and 12.247 because 23 is kind of in between 20 and 30. So the idea is you say, okay, well, it's about 12.247, and then I'm going to add the average rate of change. So I'm going to figure out how this is changing each year. And the way you do this is you take this number and minus that number and divide by this number minus that number. The change in the output divided by the change in the input. So you take 14.261 and you take away 12.247. So that's a change in the students over this 10-year period, and you divide by the 10-year period, right? 30 minus 20. All right, so the idea is you start here, and this is sort of the size of your steps, and the number of steps you take, well, you're going from 20 to 23, so you're going to take 3 steps. And so on my calculator, I can crunch this. So I'll just clear the screen. And what I can do is take 12.247, and I'll add left parenthesis 14.261, not divide by, but minus, right, 12.247, in parenthesis, now divided by left parenthesis 30 minus 20. And this is all times then 3 there. And hit enter, and out pops this answer. So this is equal to then 12.8512 million students. And so that's my approximation for what happened, how many students are enrolled in 1988. And this is called interpolation because I'm estimating inside my table. And part C, it says use linear extrapolation to estimate the number of students that will be enrolled in 2010. So 2010, this is t equals, well, 65. We started at 65. So 35 gets me to 2000. And so this is actually t equals 45. All right, so now in this problem, we're going to do something a little bit different. So let me use a different color. So now I want to approximate E of 45. And I'm not going to use 20, right? Because 45 is down here. Right? It's after 40. So what I'm going to do is I'm going to start with these two numbers. And I'll say, okay, well, it's about 17.488. It's bigger than that. And the way I find out how much bigger is I'm going to use the average rate of change. But I'm going to use the average rate of change between these two numbers now. So I'm going to do 17.488 minus 14.261. That's a change in the output divided by 40 minus 30, the change in the input. So this is going to tell me how many millions of students are changing each year. And I'm going to multiply it by, well, I'm going from 40 to 45, so I'll take 5 steps. Right? So this is like the size of my steps, and I'm taking 5 of them from 40 to 5. And then I can do this on my calculator. So on my calculator, it says, okay, you take 17.488. You add left parenthesis 17.488 minus 14.261 in parenthesis, left parenthesis, divided by left parenthesis 40 minus a 30 in parenthesis and times it by 5. So hit enter and out pops my answer. And so in this one I have 19.1015. And this is millions of students, so we should write millions. So million students. Okay. So now let's look at part C. All right, so on part C it says part D, sorry. Part D says plot the data. So let's plot this data. And I'm going to come back up here and let's erase what I've done up here so you can see the data better. All right, so now I want to plot the data. To plot the data, take out your calculator. Let's clear some of this stuff out. And now to plot the data, you have to put it in stat. So hit stat, hit enter, and then just hit over. And I'm going to put 0 enter, 10 enter, 20 enter, 30 enter, and 40 enter. And then hit over. And I'm going to go all the way up to the top. And then I'm going to hit 5.921, enter. 11.185, enter, 12.247, enter, and then 14.261, enter, and finally 17.488, enter. And once you get done here, check your work to make sure you put these all in correctly because it's easy to make mistakes. And I think they look good. And I'm going to plot my data, so go to y equals. Let's clear out this nonsense, right? Turn on your plot, so hit up and enter, and then hit down. You see my plot's highlighted. And then I'm going to go to zoom. And remember, I don't go to zoom fit, I go to zoom stat because I want to plot the things to underneath my stat button. And so here's what the plot looks like. So let's carry this down a little bit, and I can draw the diagram right here. And so what I have are these little boxes here. So I'll put one here, then one goes a little bit higher, and higher, and then a little higher, and finally a little higher. So something like that. I have 0, 10, 20, 30, 40. So label your axes. So this axis, this is the time, t, and this is in years since 1965. And then over here on the right, what do I have? Well, I usually just like to plot a couple things. So like on the window, I went from 3.9, right? So down here on the bottom, I have about 3.9. Let's put 3.595. And then up here, I have about, what, 19.45. So up here, I can put, you know, on the very top, 19.45. And now this right here, I can write as, what, millions of students per year. So let's write that as what? So this is enrollment, so E. Right, so E. Yeah, let's go back. So I'd want to label the vertical axis, and I'm going to label it E enrollment. And since it's hard to write on this thing, I'm just going to say enroll. And this is E. And this is N. Down here I write millions. Of students. Not easy to write on this board, but you know what I mean. So, students. All right, then you should title it, and then let's just title this enrollment. All right, for enrollment in colleges and universities. Okay, so that's part D, good enough. And then part E says what? So on part E, you want to use linear regression to find a linear function that will model E as a function of t and graph this function on your plot. All right, so part E, what I can do is I can take out my calculator and then go over to stat. All right, so hit stat and then go over to calculate, and then this is linear regression, so go down to linreg and hit enter, enter, and out pops my answer. And so this is going to equal, I have E, the enrollment is equal to, and then A here says 0.2621, right, times my X. Now, I'm not using X, I'm actually using the letter T, so I'll use T, plus 6.9, and then this is 784. All right, and then I can plot this on my graph by hitting y equals. Right, and so then I can say 0.2621 times x plus 6.9784. I guess I should have said I can graph this on my plot, right, by just plugging it in and then hitting graph, and you should see that the line gives a pretty close approximation. So on here, let's use green, and you can kind of see some best that we can, you know, kind of make it through this like that, you know, and then you kind of see that maybe this point down here is a little bit off the way that I drew it, so let's just redraw it. So this point should kind of be a little bit higher up, so right about there. All right, and so there's the linear function, and then there's the graph of it, and then finally Part F, it says use the linear model to estimate the enrollment in 1965. So on Part F, 1965 corresponds to time equals 0, because that's when it starts, so this term is actually 0, and so it's like 6.9784 million people. So by using the model, I would estimate 6.9784 million students are enrolled. And then finally, Part G, well, you can almost guess, since this was this number, Part G is probably that number, but let's look up and see what it says. Use the linear model to predict how the student enrollment is changing each year. And that's actually the rate of change, or the slope, which is this number. So it's changing by 0.2621 million students. And it's a rate. Right? So you have the output basically over the input, so per year. And that's 2-1. Right? So let's make sure that's clear. It looks kind of like a 4. Let's change it. So it's 2-1 million students per year. On number 19, it says, suppose you have 3 red balls, 3 blue balls, and 4 green balls in a bag. If you draw one ball, replace it, and draw another ball, find the probability of getting a green ball and a red ball. I need to change this question a bit. I really should have said here of getting a green ball in the first draw. And then a red ball in the second draw. Otherwise, this problem becomes a little bit more difficult or complicated than I wanted it to be. All right, so let's draw some pictures here. Let's draw 3 red balls. So here's 3 red balls. And then let's draw 3 blue balls. So here's 3 blue balls. And then 4 green balls. So here's 4 green balls. And notice after each draw, we are replacing this. And I have really 2 events. All right, so this will be my event A. I draw a green ball in the first draw. And then I draw a red ball in the second draw. And means intersect. So what this is asking me to do is find the probability of A intersect B. Now if these 2 events are independent, right, then I can use my formula that P of A intersect B is P of A times P of B. So are these independent? And yes, they are, because you're replacing the balls after each draw. So this is actually going to be P of A times P of B. All right, so this is the probability that you get a green ball in the first draw, and then this is the probability you get a red ball in the second draw. And so the probability of A of drawing a green ball, well, how many green balls do you have? 1, 2, 3, 4. That's 4, and there's a total of 10, so 4 divided by 10. That's the probability of getting a green ball in the first draw. And then you put the ball back in, and then you draw again, and so now we have the probability of getting a red ball, and there's 3 red balls, so it's 3 over 10. So total, you have 4 times 3, which is 12, divided by 100, which is equal to, what is this equal to? 6 over 10, right, which is actually equal to, oops, not 10, 50, right? 6 over 50, which is 3 over 25. And you can figure out the percentage on this, or on your calculator, you can do this here. Right, this would be 3 over, or I'd have it up 3 over 25, which is 0.12%. So this is or 12% of the time. All right, so if you do this 25 times, you do 2 drawings 25 times, you would expect 3 of those times to get a red in the first spot and a green ball, in the first spot, and a red ball in the second spot. Or if you do it a million times, basically 12% of the time, you'd get a green in the first spot and a red in the second spot. Okay, now we're back to numeral systems. All right, so base 2 and base 5 numeral systems. So to do this problem, we're going to want to pull up our formula sheet again. And let's start with, I guess, base 2, because that's what we start with here. So I have this base 2 numeral system. And to add in base 2, how do we do this? Well, We say 1 plus 1. You notice 1 plus 1 in base 2 is not 2, it's actually 10. So it's a 0 and a 1. And then 1 plus 1 here, again, is 10. And now if you add 10 to 1, you get 11, and that's okay in a base 2 numeral system. The only problems in a base 2 numeral system is if you get to 2 or higher. So 1 plus 1 is 10, then plus 1 is 11, so you write down 1 and carry the 1. And then 1 plus 1 is 10 again, and so you write down a 10. And so it's 1, 0, 1, 0, base 2. Right. You can check your work on these because you can actually figure out what these numbers are. Right. So this is 1, 1. This is 1, 2, and this is 1, 4. So you have 4 plus 2 plus 1. So you really have 7 things here. This is 1, 1, and 1, 2. So you have 3 things here. And of course, when you add 7 and 3, you get 10. And so this should give you 10 things. So you have 0 1s, you have 1 2, okay, you have 0 4s, and you have 1 8. If you take an 8 and add a 2, you get a 10. So that checks. Over here on this side, what do we have? Now we're base 5. So let's go up and look for the base 5 numeral system, which is right here. And so I add 3 and 3, and now I know that's 6, but in base 5 it's going to be something else, because in base 5, remember, you can always use 0, 1, 2, 3, and 4. Those are the only numerals you have. So 3 plus 3 is actually 11 in base 5, so you write 1, and you carry the 1. 1 plus 2 is 3, and plus 1 is 4. So this is 41 base 5. You can check this because you can figure out how many things this numeral represents. And so you have what? 3 1s and 2 5s, which my brain automatically says is 13. I have 3 1s and 1 5, which my brain says is 8. And then 13 plus 8, my brain automatically says is 21. And so does this represent 21 things? It sure does. I have 1 1 and 4 5s, and my brain just computes it and says, oh yeah, it's 21, right? 1 1 and 4 5s is 21 things. All right. The next problem, instead of addition, now we're going to do multiplication. Oops. All right, so on multiplication here, let's start with, it says base 2. So let's go down and go back to the base 2 tables. And so on base 2, I'm going to multiply. So 1 times 1, now notice 1 times 1 over here, sorry. 1 times 1 is 1, so I get a 1. You know, times 1 is 1, times 1 is 1. And then I put a 0 here, because I'm really in the 2 spot, so there's no 1. So 1 times 1 is 1 again, 1 times 1 is 1 again, 1 times 1 is 1 again. And then I add these two numbers base 2 again to each other. And so 1 plus 0 is 1. 1 plus 1, remember, is 10. I need to check over here. 1 plus 1 is 10. So you write a 0 and a 1. 1 plus 1 is 10. Plus 1 is 11. So I write 1 and a 1. And then 1 plus 1 again is 10. So I write a 1 and a 0. And that's base 2. And then on the next one, I want to do it base 5. And so I'm going to go up here and pull up the base 5 multiplication table. And so I do 3 times 3, and 3 times 3 is 14, so I'll write a 4 and a 1. 3 times 2 is 11, and I'll add 1, and I get 12. As long as I don't pass, 14 in a sense of 4, I'm fine, okay? And so now I put a 0 here, and then 1 times 3 is 3, and 1 times 2 is 2, and then I add these two numbers together. And remember, these are base 5, so 4 plus 0 is still 4. Now 2 plus 3, now that's 5, right? So now I'm in trouble, so I have to look over here. So 2 plus 3 is not really 5, it's actually 10, base 5, so that's a 0 and a 1. And then 1 plus 1 is 2, plus another 2 is 4. So I get 404, and that's base 5. So that's my answer. You can check these. One way to check these is that you'll figure out what number of things this actually represents. So 3 1s and 2 5s, that's actually a 13. 3 1s and 1 5, that's actually 8. So that's actually 8 times 13, which you can actually do on your calculator if you want to, but that's 104. Right? 8 times 10 is 80, plus 24 is 104. And check, is this 104 things with 4 1s, 0 5s, and 4 25s. And so 4 25s is 100, plus 4 is 104. So it checks. So you can actually check it if you want to make sure it's right. The next problem, number 21, we're back to financial mathematics here. It says Gina put $3,500 into an account that compounds interest quarterly. What nominal interest rate must she have to double her money in 7 years? So we have $3,500, compounds interest quarterly. What nominal interest rate could she have to double her money in 7 years? So I got to figure out which formula do I use. So let's pull up our formulas, our financial formulas. And they're all the way down here at the bottom. All right. So some of you can kind of cross off, right? It's not the simple interest formula. Now, it could be the compound interest formula. And you come down here. It's not the continuous, because it would say continuous. And it could be the financial value annuity formula, I guess. And it's not probably the balance formula, because it's not talking about number of payments, you know. And then I realized, oh, yeah, and it's not talking about payments here either. Right? It's actually just talking that she makes a loan, compound interest. How long will she have to? What is the nominal interest rate must she have to double her money in 7 years? So there's no payment talk here. So I'm gonna make a guess here and say it's the compound interest formula. So the first thing I want to do is write down future value equals present value 1 plus I over n to the nt. And then I am going to close this, and I just want to plug in the value. So present value is how much you borrowed, so or put in the account. So that 3,500 went into the account, so 3,500. 1 plus the interest rate is 0. Oh, and that's what I'm looking for. Right? So I have to erase that. That's actually going to be I. Right? So and the way I found that, I was looking for the interest rate, and I can't find it. So that's actually what I'm looking for. Then n is the number of times I compound the loan, which is quarterly, so that's 4. And it's raised to the 4 times t, and t is the time, 7 years. And then I should be able to find the future value, and that comes from how much it takes to double her money. So double is 2 times the original amount, so that's 2 times 3,500, so that's 7,000. And now I have it. All right, so I'm going to graph the right, graph the left, and intersect. So let's pull this up and move it over here. Hit y equals, clear this out. Turn off your plot if it's on, because that'll mess things up. So now my plot's not on. First I'll graph the formula, so 33,500, left parenthesis 1 plus, and then I have my I, which I make x, divided by 4, in parenthesis, raised to. Now if you want to put 4 times 7 down, you have to put that in parentheses, but I know 4 times 7 is 28, so I'm just going to put 28, hit enter, and then in y2 I put my 7,000. And then I'm going to go to my window. Now for my window, I have to ask myself the question, what am I looking for? Well, I'm looking for I. And I is interest, and interest always lies between 0 and 1. And then I'll do zoom fit. And so I should get a graph. So I'll draw this 0 and 1. And that graph is actually way, right, here's the formula on the right. And you're going to see down here, there's the 7,000 way at the bottom. All right, so way at the bottom down here, and I'm going to intersect it. So I do second, trace, go down to number 5 for intersect, hit enter 3 times, and out pops my answer. I is approximately, oh, and it's hard to read that number, okay? So now I got to figure out, you know, I really don't know what that number is because I can't read it off there, and so I can figure it out if I change my window. So I'm gonna have to move my window, and the way I can move my window, there are several ways to do this. I mean, one way is to actually change, you know, what y max and y min are. I can move it up or down, but I'm actually gonna change my my 0 to my x max, because really, you know, it's probably somewhere between 0 and 0.2. So I'm going to try that first and see if that works, if I can see the answer from that. I really don't need to go to 1. Right? 1 is 100% interest, which basically you're never going to get. So let's try 0 to 0.2 and see if that gives me an answer where I can see it. So I'll make my window a little smaller. Right? So if you want, I can go from 0 to 0.2, and now I can intersect it, and you'll be able to see your answer. Whereas before, I was kind of blocked by the curves themselves. Oh, and there I see it. Now it's 0.1. Right, so the interest I is approximately 0.1, right? Or you could write 10% here. So I'd probably the answer I'd write down is 10%, although you'd take 0.1. Number 22 now. Number 22 is asking us, are these permutations or combinations? So remember, in a permutation, right, the order matters. Whereas in a combination, right, the order doesn't matter. So to answer these questions, I say, okay, does the order matter in a driver's license number? And certainly it does. So this is an example of a permutation. Right, permutations and combinations are just arrangements, right? Permutation is an arrangement of some numbers, some letters, or whatever, in which the order matters. And a combination is an arrangement of, again, letters, numbers, or whatever, in which the order really doesn't matter. An area code, well, certainly the order matters in an area code. If the area code's 479, like it is here, and I change the numbers and write 749, that's going to be different. So here, again, is an example of a permutation. So this is a permutation. I guess it's not plural, so you only need permutation. And then the last one, of course, is probably a combination, and it is. It's a grocery list, and in a grocery list, the order doesn't matter. So this is an example of a combination. And so in permutations, order matters, and a combination, and order doesn't matter. Another way to remember this is in a combination lock, the order matters, right? So a combination mathematically is sort of the opposite. In a combination mathematically, we say the order doesn't matter, whereas in a permutation, it does matter. So it's kind of like, remember it by the opposite.